better.
So what was the best attended conference?
Well, the one that I chaired in Maui was 350 people.
Wow.
But
Well,
it was Maui. It was early on. It was halfway between Japan and the United States, which is where the principal efforts were, so it was relatively easily accessed. This one is well attended because it's in the center of America and people can drive to it, and the dorms make it cheaper and money. The next one will be in Venice.
Venice, Italy. Fabulous.
15th of March to 21st of March, 2015.
Okay.
So it's quite a way away.
2015.
Right.
Oh my God, there's going to be a lot to talk about then.
Well, it's part of the problem. You know, punching them out every 12 months, people haven't had time. We're not well enough funded. The research groups are not large enough to actually generate new material in that time. So people that have to talk wind up saying the same things.
Okay, so that makes sense. Well, let me ask you about, you've been around the world representing the cold fusion community in the US, really, internationally. And can you talk about the, comparatively speaking, the research internationally and compare it to the research in the US? Is international research moving ahead quickly comparatively to the US?
I don't see it quite in those terms, and we recognized some time ago that we wouldn't make progress as a community unless we formed constructive collaborations. So I went out of my way to set up collaborations with a number of institutions, with Peter Hagelstein at MIT, energetics folks in Israel, but before that, Enea Frascati, Vittorio Violanto, and before him, Franco Scaramuzzi. So I was collaborating with those guys, actively flying backwards and forwards for, it's too many years. It's since the mid-1990s, I suppose. So I don't separate the Italian international activity from ours. It's the same. We are part of the same research group. So Vittorio does the metallurgy side. I do the electrochemistry side. Peter does the theory part. So we're subcritical. And it's better this way anyway. I mean, people want to stay with their own institutions. So the Enea group is extremely good, extremely capable. They're young people. I was just thinking today that I began collaborating with Vittorio when he was about the same age as Emanuele, who presented today, who Vittorio is tutoring and bringing on. So it's the second generation, but they don't have consistent funding. They could have done much more. Hopefully, we'll spring some money from the European Union to keep that effort stable.
You recently were at a meeting with the European Parliament. Can you talk about what happened there and their interest?
Certainly. We've been trying, Vittorio and I particularly, but others as well, to get money out of the European Union for a number of years, probably 4 or 5 years, and Enea is supporting this thrust to the European Parliament. About 18 months ago, maybe 2 years, they invited us to talk. Rather than us having to beat on them, they invited us to present. So we came. Rob Duncan. Rob Duncan and I represented the United States, Vittorio representing Italy. We had industrialists along, several of them. One of them, who in fact will be the chairman of the next ICCF, Professor Antonio Lagatta. So Tony was there. Some of the people that are here. So we went, we talked, blew them away. We were a little bit too technical. We lost half of the audience before we got to the end, but they were probably the people that weren't interested that much in the first place. But the rest of them were completely enchanted with what they heard. An intelligent, reasonable, well-designed research program directed towards a primary energy source that had the potential to do something about environmental concerns, which is what these people were interested in. So we went away. We didn't get any money. We didn't even get any hints at a proposal. But quite recently, we were invited by the Materials Committee. The chairman of the committee is Herman von Bose. He is responsible for, chairman of a committee that has a $60 billion materials science budget. We were invited there. We went. We presented to a room full of people. And they had to stop accepting reservations for the meeting. So 85 people sat up. We presented. Von Bose stayed through all of it. Told us what we needed to do in order to apply for funding. Encouraged us strongly. So I think something will come out of that initiative. Probably, I'm not going to get any money directly, but I think that Vittorio and his team at NEA will get funding, and that we may set up a research activity in Europe purposely dedicated to this problem, involving some other industrialists in Italy. So in the perfect way to operate it, and there's some possibility that this will happen, is for the European money to be offered, and we can use that as an argument to the US governmental agencies to participate. So I think it will encourage Department of Energy, for example, who really should be involved in this area, to put funding in. We can say, look, the Europeans are doing it. This is what they're putting in. This is what it's for. If we want to be, you got to pay to play. If we want to be privy to the information that's going to be gathered in this activity, we need to have some players in the United States, and we'll form a consortium, a research consortium. So I'm encouraged. It's governments are hard, they're slow, they've got funny rules, but certainly the Europeans have a very good perspective on this and understand that this has the potential to solve a real world problem.
Italy has just been a hotbed of activity from early on. What is it about the Italian scientists that makes them so successful?
It's a good question. They are very, very good, and not as afraid of thinking outside the box as the United States. It may be something to do with their funding system. It may be tenure, I think, is more of a real operational condition in Italy than it is in the United States. There is no true tenure here. And if you fail to get funding, you will fail to have students, you'll fail to have a job. Certainly you'll fail to have promotion in the United States, whereas in Italy, once you achieve a tenured position, you're there for life. You can do what you want. You can be relatively unafraid in exploring new areas. It's how it used to be in the US. Certainly was the British tradition, but it isn't true here anymore. So you notice that the Cold Fusioneers are all old guys. Why old? Because they've already established their careers and reputations. They don't need to publish in order to advance. We can afford to take risks. I'm a young man in the cold fusion community. I'll be 65 this year.
In Italy, there is also a history of industry involvement as well. Can you talk about that industrial involvement? For instance, Fiat was involved for many years.
And wants to be involved again. They got out, a lot of it's driven by personalities, and individuals in these organizations are interested, so they drag their corporations along. The Fiat interest was largely promoted by people that Giuliano Preparata had trained. So they were very impressed with Giuliano's ideas. Giuliano had some spectacular ideas, and he was very charismatic and very influential on certain individuals. So the Fiat activity was pretty much just Giuliano's enormous personality. But I think the Italians are pragmatic. They do understand the value of science as a precursor to innovation.
Let me just switch gears a little bit here. You've lost some very good friends and some colleagues recently, and what do you think about how does that make you feel when you know that that you are getting closer to seeing the fruition of all this research, and yet some of these people will miss that?
Well,
at least on this plane.
I would love to have had a clear resolution of this matter before Martin, left us, and we didn't. He will never get a Nobel Prize. You can't get a Nobel Prize posthumously. He deserves a Nobel Prize. That makes me sad. And we worked hard sort of to keep him alive and keep him sentient, actually. But we did have a wonderful opportunity with Martin. The award given to him by Minoru Toyoda, or in Minoru Toyoda's name, organized by Akito Takahashi and Vittorio Violante in Rome, at the very top of Castel Sant'Angelo, overlooking the Tiber and overlooking the Vatican. It was a beautiful night, and he was there. He was conscious. He was able to receive it. He was well aware of of the esteem of the people around him. So that was nice to find a way to provide fitting tribute. And you can't live forever. And he was getting tired. He was getting run down. So this is the cycle. John Barker's pretty much the same. I was involved with John in an increasingly strenuous debate up until virtually the day that he died. And his mind was still going. He knew what was going on. He'd become physically unable to travel, so he wasn't able to come to these meetings. But sad, yes, unfortunate. But how did that affect the field? Well, not at all, really. They weren't practicing the art, and hadn't been for a decade. So you can hang on to these attachments, but and when I first knew John Barker, for example, he taught me everything I knew, essentially, and I had nothing to offer him at all. And conversations with John was me shutting up and listening. But in the end of his life, he'd slipped sufficiently, and I had gained sufficiently that we had a sort of an equal participation, and that was a very good thing. So I'm just happy, not happy, but I'm not sad, except for me personally, a selfish sadness. But the passing of Martin and John is the way it is. Ken Shoulders is a slightly different case, because Ken was so private and knew so much that was so important and so unbelievable, actually. So I am very nervous that what it is that Ken contributed by way of knowledge about these clustered electrons will be lost. That knowledge will be lost without him pushing it along. He was the only one doing experiments in the area. He was the only one that knew the implications of what he had discovered. And the implications are profound. So Martin and John, you can say they left with their job done. Ken, I think, did not leave with his job done. Didn't have anybody to carry on.
When you see young people entering this field, such as the Martin Fleischmann Memorial Project, how does that make you feel?
Well, it's good, of course, and young people must enter the field. We had the International Advisory Committee meeting, the IAC organizes the sequence of the conferences, and I looked around the room. I've been to every one, which is a triumph in itself, in a way. When we first had our first conference in Salt Lake City, the critics said, "Well, there won't be another one." Well, there was another one. Well, there won't be three. There was three. There are 18. We planned the 19th. But that's the good news. The bad news is that the people doing the planning are essentially the same people, 25 years older. So we absolutely need to get young folks involved. The activity of the Martin Fleischmann Project, Martin Fleischmann Memorial Project, I admire their enthusiasm. They are learning on the job. What I haven't paid that much attention to them, and they're not trained in the disciplines that I trained in. I think there's some learning to do, some experience to gain, but the fact that they're doing it is spectacular. We had a meeting with a number of the students here at the University of Missouri last night, career opportunities in cold fusion, and a dozen students or so sat through us old guys telling them how to make their careers, and very, very intelligent kids, interested and enthusiastic about getting into this area. They'd love to be in it. They're worried about the career suicide myth, actually, and but if we can capture a few of them, it doesn't take many. I mean, Vittorio has 2 young people with him at this meeting. They well trained in just exactly the right disciplines. The chairman of the next conference, it will be a young man. He will be, I guess, in his 30s. So the times now are changing, and we are moving in the younger direction, as we must. For this field to be truly successful, it is going to take the energy that only young people have. I was very impressed with the panel of industrialists that Matt Trevithick put together. The energy, the enthusiasm, and the not only youth but modernness, and the modern approach, venture capital, in the way that businesses really are run, rather than how old scientists imagine that the businesses might be run. So if I were to sum up in one word what has impressed me about this week, it's the participation of young people.
Given the fact that a lot of schools and institutions, at least in the US and around the world as well, have shunned this research and kind of not allowed these opportunities for students, the idea of apprenticeship and something like what the Martin Fleischmann Memorial Project people are doing, and getting tutored on the job by people in the field. Do you see that could be a new paradigm for getting involved in this field by young people?
Yeah, very possibly. And it's come about for the worst of reasons. I mean, there has been a very cynical effort to prevent advancement of this field by preventing publication. It's a nasty, dirty tool, and by not allowing publication, you prevent anybody who ever intends to be an academic from entering the field. So the young people have been kept out by the academic pathway from participating, so they need another way. The industrial pathway, if Jeff Callion is correct, Rossi is correct, if the Berlin we're working with, if we can go the industrial route and show that there is something of real commercial value here, then the young people can get involved on an engineering side, a business side, marketing side, whatever. They don't have to get involved in the academic way. We will have to go back and do the research. The research isn't all done, barely begun. So the science is inevitable must happen, will happen, has been delayed, as I say cynically. But we can go back to it afterwards. We may need to go back to it at the time that nuclear products are offered for sale to the public. That's something that is irresponsible if you don't have a full understanding of the mechanism, and we don't have a full understanding of the mechanism. But so the science will have to be done to support the industry. But I think that's always the case. I think products are engineered into existence before they're understood. And we work with things every day that we don't understand. The lead-acid battery in your car was operated for 100 years before we had a full understanding of the exact nature of the electrochemical processes, and we're still discovering things. So engineers just do it, roll up their sleeves, make something, put it together, test it, and test it better, and the science comes along later. So I think the academic boycott, the barrier that's been imposed by the academic route, which a lot of us have been butting our heads against. I tried to science this thing into existence, or help science this thing into existence. Is there an effect? Yes, no, yes. What are the conditions under which you observe the effect? And working mostly with public sponsorship, encouraged to publish, was more or less prevented from publishing because of the fear that had been instilled in the editors who didn't want to publish. And it's really, I used to be an editor of a scientific journal. It's really easy to get something not published. You send it to somebody who you know will not accept the paper. Trivial. So you justify. It's not your decision, it's the decision of the people that you sent it to, and you get to choose who those people are.
Well, let me ask you, because the industrial side seems to be happening. It appears as if we're moving closer in the field with these entities like Defcalion and Rossi coming out with their proposals and demonstrations. And there's these varied types of systems. Do you see certain types of cells as more scientific research, and then other types of cells as more commercial types? I'm thinking of the palladium and deuterium, and then the nickel hydrogen. They seem to have different types of functions. Is that true? And can you talk about the differences between those types of systems and their function as scientific research and or commercial potential?
Well, the commercial potential of palladium is limited by the availability of palladium. That's it. It's a precious resource. It has strategic needs. If we start to use a lot of it, its price will go up. At the moment, palladium is a byproduct of the platinum industry. Basically, they occur together, and you have to separate them in order to sell them as pure elements. And they could afford to give palladium away. Once upon a time, it was $60 an ounce. It went up in price to $1,060 an ounce on the backs of catalytic converters and cars. So that's a huge gain in price. And that's small compared to what it would take if cold fusion generators required palladium. So the palladium system is limited. I think when we understand what we're doing and understand what we're seeing, it will turn out that there's one underlying mechanism, and I think it's highly likely, just based upon our own experimental evidence at SRI, I think it's highly likely that nickel and palladium work, and therefore very plausibly other metals, and that deuterium and natural hydrogen work, as Rossi or Piantelli first, and then Rossi and then Defcalion have claimed. So I don't know yet whether It is the hydrogen, the protons in the natural hydrogen system that is providing the heat, or the deuterium fraction of natural hydrogen that is causing this effect. There's plenty of it there to do the job. So I think it'll be horses for courses. I think for specialized applications, high power, high price satellites, and the things that made fuel cells viable, things where you absolutely need a power source to last a long time, can't afford to carry much weight, but your price doesn't matter. I think the palladium system will have some application there. But the palladium system provides a very powerful workhorse because we understand it better. Far more research has been done in the area of the palladium deuterium system than the nickel natural hydrogen system. So a lot of our learning has been obtained there. There are people who say that that's all irrelevant, and that you should be focusing on the nickel natural hydrogen system. And if I were in Jeff Callion or Rossi or Brillouin's shoes, I would be focusing on non-palladium systems, just because the product that I'm seeking to make cannot be made economically with palladium. So nickel, great. Poor man's palladium, highly likely to work, seems to work great. But the learning that we've obtained in the deuterium palladium system is I think, crucial. It's got us here, and I think it will continue to be very, very, very important because it's a much better defined system.
You've spoken publicly about this field for many years, and I've seen one of your slides where you've had a list of various names for this reaction. What is your favorite name for this reaction, and how do you feel about the level of knowledge of the public about the word nuclear and their fear of the word nuclear, and how does that affect how you name this reaction?
Well, I didn't use the name cold fusion publicly until quite recently, really, until I knew that it was fusion. And now we have evidence for fusion, helium-3, helium-4, tritium fusion products. When it's all determined in the end, it will be clear that fusion will be part of, if not completely all of the nuclear energy generating reaction. So I'm not afraid of using cold fusion. Martin's death actually inspired me to use it proudly. So he called it cold fusion, I can call it cold fusion. It doesn't matter really what it is. It's not a scientific designation, it's a name. People call me Michael, what does that mean? It's cold fusion. That's the name, it's understood, it's easily communicated, everybody knows what it is, and if you try and hide it and pretend you're doing something, low energy nuclear reactions. I don't like that phrase. It's again another one that's very widely used as a way of avoiding the fusion claim, but it contains two bad elements. Low energy, and it's not low energy. We don't want it to be low energy. It's low intensity perhaps, but the energy density of these reactions is very high, and the energy that we put into it per unit volume or unit area is high. It's a low temperature nuclear reaction. Even that's not a very good thing. But the nuclear part is just not a great place to go, and it's not societally well accepted. And as the public gains more information about what really happened at Fukushima and what the consequences of that will be in the Pacific, nuclear is going to become even less and less loved name. But that naming business is a problem. In every meeting I've had on this subject, every meeting I've participated in, somebody has said, well, cold fusion's such a bad name, we need a new name. So people are always trying to name it, and the worst people are the people that have a name of their own because they defend it like their children. So on the one hand, it doesn't matter what you call it as long as people understand what it is. We sat at one of the International Advisory Committee meetings in Beijing, actually, with a bunch of very intelligent people, all of the IAC and some extremely senior people from China there. What should the name be? And I think it was Peter Hagelstein who finally constructed the acceptable phrase of condensed matter nuclear science. Still has the nuclear in it, but it is, CMNS is how I think of it. It just doesn't roll off the tongue very well. And I increasingly call it cold fusion, and partly, as I said, because of that's what Martin called it. Why shouldn't I? And partly because of the pushback against it, and people are arguing it's not fusion for purposes of their own. So you know, damn them.
You know, the fact that this is a nuclear reaction does scare the public, or the idea of nuclear reactions. Can you talk about how cold fusion as a nuclear reaction is different than the kind of nuclear reactions that the public is really aware of?
Yeah, certainly there are no energetic products. That's unfortunate for us, because if the products were more energetic, they would be more easily observed. But it's absolutely perfect for society, because we don't want technologies that produce radiation and neutrons. And the reason the tokamak will never succeed as a commercial power source is one of the reasons, there are several, is that the neutrons that are produced are highly destructive. They just wear things out very fast. You've got to stay away from them. You've got to treat them in special ways. So high energy products in commercial application are not the way one would go if one had a choice. Commercial nuclear, conventional nuclear, fission power, well designed, well situated. You know, if you put it not on an earthquake fault, or put it not where tsunami is likely to hit, you put it in a dry area where accidents are inevitable, aren't going to cause any problems. You can remediate it. It's a very nice form of power. I worked in conventional nuclear power for years, designing sensors and monitors to keep reactors safe. It's benign. It doesn't cause as much heating as burning hydrocarbons. It doesn't squander a one-time resource of hydrocarbons. It doesn't produce CO2. It can be used to capture CO2. So I'm not an opponent of conventional nuclear power. I'm an opponent of doing it on minimum bid and situating it in stupid places. But in my mind, there need not be anything against nuclear. It's a high energy source. High energy sources have risks associated with them. Those risks ought to be monitored. But you're right, the public is not quite as well informed as I am perhaps on this subject, so that their nervousness is a consequence of some very bad PR and some rather stupid decision making.
But I mean, isn't it true that in conventional nuclear power we have to use radioactive materials, and it creates radioactive waste? Isn't cold fusion when it will be a technology, wouldn't that be much cleaner and much safer?
Much cleaner and much safer, yes.
Can you describe how clean is cold fusion?
Well, I don't know. You see, we don't know. I'm probably not going to give you the answer that you want on this, because we don't know. We haven't scaled it up yet, you know, and we don't know what it is. And when we scale it up, some surprises could easily occur, which is why we need to know about the science first. So I am not going to put my hand in my heart and say to you unquestionably that there will be no hazards associated with the development of this technology. But as it stands right now, as it looks right now, the products that I am aware of are helium-4 and helium-3, which are benign. They're useful, actually. You could sell the helium-3 if you were making it in any quantity. It's an inert gas. It does nothing, and if you let it go, it would simply drift up and leave the Earth's atmosphere. So, great. Tritium. There's a little bit of tritium produced in some of these experiments, and that could get more. But of all the radioactive species that I'm aware of, tritium is probably the most benign. There's a very low energy beta, so it doesn't do much harm. And it's got a relatively short half-life, and some of the products from conventional fission power have half-lives of hundreds of thousands of years. So 100,000 years from now, there's going to be a half as much as there is now. That time scale for tritium is 12.5 years, so you can decay it into non-existence even if you didn't have a use for it. So it's easily sequestered, gathered up, and if you accidentally contaminate yourself with tritiated water, for example, the medical relief for that problem is a case of beer. You just pee it out of your body. So it is, tritium. If that's as bad as it gets. Some low energy X-rays. So far we haven't seen anything that scares me.
Good. I forgot what I was going to ask next. Oh yeah, you talked about the one-time source of fossil fuels, oil.
Mm-hmm.
Are you aware of peak oil, and do you accept the tenets of peak oil, if so?
I am aware of it. I have friends that are deeply involved in this. I'm not personally or professionally involved in it. I don't think that that's something that our generation needs to be concerned about. I think that peak will move out, and the peak is somewhat artificial. Oil companies only bother to survey out to 30 years because that's the longest that their financial projections take them. There's some argument that the oil is not, as one of my friends used to say, dinosaur dung. It's not. Its origin isn't biomass. That it is in fact an inorganic reaction that occurs deep in the earth between water and carbon dioxide or carbonates, with plenty of which. So maybe the oil will keep coming for a long time. We've got a lot of coal. So we do have a lot of time to solve this problem.
Isn't coal contributing to the CO2 levels though? And that's detrimental, and this is one of the reasons why we need cold fusion. Isn't that true? Would you agree?
I'm unconvinced by the arguments for anthropomorphic CO2 as a problem with climate. I studied them, and I worried about it, and I have enough science to at least begin to model it. I started to look into it, and the evidence isn't in. Although the people have been well convinced by a very effective PR campaign, I don't know that man-made carbon dioxide is really as much of a problem as is claimed. So that one doesn't worry me. There is a problem with CO2, which I think should be addressed, or at least thought about more deeply, is that the CO2 is dissolving into the oceans and causing acidification and etching away of coral and changing the species. So that one does worry me. But the climate change argument, I think that's pure popular. It's an argument that's made to convince the people of a certain course of action. It's PR.
Okay, let me switch gears a little here and ask you about, you were featured in the 60 Minutes segment back in 2009. Cold fusion is more than junk science, it's hot again. Hot again, right? Yes. How did things change for you after that? Was there more interest in your work after that aired?
I did get a lot of calls for the first day or two, and the attention span seems to have been like a day. And I didn't think any of the calls turned into anything. But over time it's built up. People are aware of it, are aware of that, and people use it in discussions supporting why we, and the meeting we had in Europe, for example, that was one of the reasons that they had the meeting and invited me to the meeting, and Rob Duncan. I'll tell you one thing that documentary did, which has had lasting effects on the field and will have powerful effects in the future, involving Rob Duncan in the field. That got Rob involved. I had the task, or partly my task, to identify, one honest physicist who wanders around with a light looking for one honest man. I had to look for one honest physicist, not such an easy task. And we had at least a half a dozen names, high focus, high profile names, people whose names that you would probably know, either volunteer themselves or proposed to act as the independent observer. What we needed on the program was somebody who was not associated with cold fusion, who could evaluate the data and make a judgment on camera. We found at least half a dozen people who were willing to do that, but they didn't feel the need to review the data or see the experiment. Their opinion was already formed, so they're willing to take the money and do the piece, go on air and state the absolute ridiculousness of this, but they weren't willing to read the literature or travel to see the experiments. So we found Rob. I didn't know Rob at the time. He came highly recommended. He had one element of his background which at least encouraged me, in that he had been a calorimetrist, and his early days were spent in calorimetry. Everything that I could learn about him in a day or two that I had to review this information was positive. And it turned out he was much, much better than I had even estimated that he would be. We did take a bit of a gamble with Rob. We didn't know what he was going to say. He didn't know what he was going to say, and that's important. He didn't know what he was going to say until he evaluated the data. So we sent him papers, he read them. He was put on a plane, taken to Israel, looked at the experiment, reviewed what they'd done, talked to the people. He had enough experience with the LabVIEW programs that they were running to know more or less exactly how the measurements were being made and therefore what they meant. He's an experimentalist, a practical guy, very good. And he did his due diligence, he did some calculations, he did some thinking, and he said what he said on television, and then didn't stop there. He went to the Pentagon, actually, and said, I've just been introduced to this field, and there is something there, and we need to study it, and got a commitment from the Pentagon's science officer to fund this field at a level of $30 million. Ultimately quashed by DOE, who said, we would rather you didn't do that. But Rob puts his money where his mouth is, if he sees something, he says something. I once introduced Rob here, actually in Missouri, at a conference that he put on, as a very unusual man. He has an open mind. He's capable of changing it. And if he changes his mind, he's willing to state that publicly. And so he came back here and encouraged the professors here at this university, and Sidney Kimmel, a friend of mine who had been funding the energetics group, more or less by himself, without much prompting, decided that he would, on the basis of Rob's intellectual honesty and attitude and openness, move his research activity from Israel to an incubator on this campus. It's then subsequently been folded into the Sidney Kimmel Institute for Nuclear Renaissance, but that's all on Rob. and that's all from the 60 Minutes program. So, and that continues to bear fruit. He's now a member of our International Advisory Committee, a strong force in the field, both leadership and actual technical boots on the ground research. He volunteered to host this conference, ICCF18, put together the best proposal we've ever seen for the conference, was really serious about it, and then did a really serious job. So that's huge, inestimably large. So I would say the very best thing to come out of the 60 Minutes program was Rob Duncan.
Well, my next question then is, are there plans for another 60 Minutes episode?
They will do another one when there's something clear that needs to be spoken. I know they are monitoring the field, and they're watching for it, and are open to input as to when is the right time. Now is not the right time, although if this demonstration that Jeff Callion put on television here is verified and validated, so that it is certain that it is so. I'm hopeful that Jeff Callion are right. I don't see anything wrong with their setup. I've never seen their setup except on a computer screen. But if we get to the point of being absolutely convinced, then 60 Minutes would get back in. And some of their reputation attaches to this, and they went out on a limb. They would like to come back and say, see, we were right and we were ahead of you. They would do it. But I don't think the time is quite right.
Let me ask you about the field itself, and we'll be wrapping up soon. How are you doing on time?
Oh, okay. I got plenty of time.
Okay. The field itself, there's so many people doing various kinds of experiments, different types of cells, measuring multiple different types of effects. How do you kind of rein all that in to some kind of consensus, so there is some kind of strong message that someone like 60 Minutes would, can seize upon this, here's an achievement right here. How can you take all those varied viewpoints and get consensus?
Well, you can't get consensus, and the people in this field are strong-minded individualists. You can't get them to agree to anything, and we have self-selected. We are confident of our own opinions, and I don't even attempt to. On rare occasions, I'm obliged to, but it's hard work. So, consensus is not what we're looking for, and in consensus, you shut out ideas and opinions, and this is a sufficiently young field. In fact, it's barely born. You don't want to shut out ideas. We can't slam the door on anybody. And it's one of the things that makes it fun, and one of the things that makes it frustrating is, some wise man said, it ain't what a man don't know that makes him a fool, it's what he knows that ain't so. And something we know absolutely with certainty that our teachers have taught us and our textbooks reinforce, something that we know about physics at quite a fundamental level is wrong. So how do we prune, and how do we converge? How do we achieve consensus? If normally you do that with certain sets of rules, and I, for example, will not accept anything that violates the first law of thermodynamics. In part because my calorimeters rely on the first law of thermodynamics. So if it violates that, I got a problem. But I don't know that I hold any other law in such high regard. So achieving consensus is hard, I argue impossible in this field, and that I don't think we should try and do it. There is an issue. As the field gets broader, the publications get more numerous, and the number of topics covered gets larger. I think the only man who certainly the only man who claims to have read every paper in the field is Ed Storms. Ed said he's read all of the 2,000 papers that are in the Lehner Kanner website. I believe him. I haven't. And if I had, it wouldn't do me any good because I wouldn't remember what was in them. So I think Ed will be the last man ever, and the first two probably, to legitimately claim to have read and mastered every paper in the field. It will become increasingly impossible as the field diverges into new territories and the papers increase in number.
Do you think that this reaction is actually going against some of conventional nuclear theory, or do you think that you have this conventional nuclear theory from 100 years ago, and that maybe something is missing that cold fusion will it'll expand that theory? What do you think?
Well, it's a guess because I don't know. In the early days of this field, I didn't know very much nuclear physics, and I have a PhD in physics and chemistry, but not nuclear. I would really never focused much on the nuclear side of it. So first thing I did was go and talk to my nuclear physics buddies. What is this? How is this possible? I figured out the Coulomb barrier, and within a day or two I was aware of what is conventional and how different this must be from conventional. But when I went to speak to the textbook physicists, the low-level guys who had learned from textbooks, they all told me it's impossible, ridiculous, Coulomb barrier, can't do it, spacing, never get there, it doesn't happen, no way, no how. They also told me things that I now know to be absolutely wrong, and they claimed that we knew everything there was about the fusion reaction from high energy interactions between deuterons at millions of electron volts, and that scaled down to zero, that from studying it at 10 million and 1 million you could extrapolate down to zero. So they knew what would happen at low energies. Turns out they were wrong. I mean, the branching ratio does change, the interaction rate does change, and I don't know if that's relevant, but I do know that something that I was told by those guys was absolutely not right. They had no right to say it because they didn't know it. They were guessing. They were out of their field, out of their territory, out of their energy range, and when the experiments were finally done, it turned out that what they had told me was not right. I don't know how relevant that is, but when I went to speak to the people who had done the experiments and were instrumental in discovering the laws that were then transcribed into the textbooks, and textbooks are written as simplifications. We make it simple so we can teach our children. Even the equations used are truncated in terms. We know there are additional terms in a lot of these important equations. We just ignore them because it makes things too hard to teach. That becomes dogma. Dogma becomes the simplification. But the guys that had actually done the work, Teller, Schringer, they had no problem imagining how this could be. They knew that what was accepted as the rule had enough variability and uncertainty to include the effects that were under discussion. Schringer just sat down and started calculating, and he said, well, yeah, we could do this. If we put two deuterons or a deuteron and a proton inside the octahedral and increase the amplitude of their vibration by 30%, just 30%, you would account for this effect. Now, not easy to do, but it's a long way from not easy to impossible. And Teller also, he said to me, well, from the evidence that you presented to me, I don't think that this is a cold fusion effect, but if it were, it would be easily accounted for in the uncertainties of physics, and it will turn out to be nuclear catalysis at an interface. And it will turn out to be nuclear catalysis at an interface, and I didn't pay that much attention to him. I didn't really understand what he was saying. I didn't know how to make use of that information, but the guys that knew their stuff never had a problem with it. It's the guys that learn from textbooks who tell you it's impossible.
You mentioned, there's episodes that recur throughout history. Do you think that the rejection of cold fusion has had more to do with that, kind of blinder to this theory by textbook type people? What do you think is that mentality that differs? What mentality differs between a textbook writer and then the person that's, hey, why not? I'll entertain this idea.
I honestly don't know why people tell you things with absolute certainty when they're not absolutely certain. I think they're out of their comfort zone, and there's a really serious issue here. If it turns out that the way that Martin and Stan discovered is a more easy and direct pathway to practical fusion, then a whole lot of people will have spent a whole lot of money and a whole lot of career doing the wrong thing. And that's hard to accept, that you've spent your entire life chasing something which is probably impossible, but it's certainly not the easiest way to do it. So a lot of people made very public comments in the early days, very public, absolute statements, which if proven to be wrong, will destroy their reputations, and particularly at the end of their careers. You live on the reputation that you've achieved before, and if it turns out that some of the things that you're closely associated with are just not right, then you lose bragging rights with your friends, but you also lose income. People don't consult you anymore. So there's a risk, and I think a lot of the people that have opposed us have just been trying to forestall the day, stave off the day at which it is known that they are wrong. And it's taken us long enough that I think most of them have probably achieved their goals.
Well, let me just ask you just a general question about the benefits of this for our world. If we can make cold fusion a reality and bring this technology, what do you think will be the biggest benefits? Well, what are some of the benefits, and what's the biggest benefit?
See, I don't have an answer to that. I don't know. We're doing research. If it turns out that the very best thing that comes out of this is hot water for your bath, I will be very disappointed. Now, it turns out that 40% of all of the world's energy is used at 80 degrees centigrade or below. So that even the systems that have been demonstrated today could, if used, could save us 40% of the hydrocarbon consumption. You could say that's a benefit. But we've discovered that nuclear physics occurs in condensed matter in ways quite differently, with different products and different rates, from the way that it does in free space. So we can wield the power of nuclear physics on a tabletop, as I often say. And if you can do that, you can do a lot of things, and I'd hope that you could do a lot more than heat water, make Douglas Morrison his cup of tea. I don't know. See, I don't know. Until we understand it much better than we do now, have a good model for the basic physics that underlies this effect, we will not know what the product is. But I'm willing to stake my limited reputation on the fact that the final and best use for mankind will have nothing to do with heating water to make Douglas Morrison a cup of tea.
Can you just tell us the difference between chemical energy and nuclear energy?
Now, the reason nuclear is exciting, the world needs a new primary energy source. What does that mean? Primary means that it is not stored. It comes from something that already is. So coal is a primary energy source. Not really, but in practice it is, because the coal beds already exist, so we can burn it, we get energy. We need that. Civilization needs that. So the world needs a new primary energy source sometime. And nuclear is so much more attractive than chemical because the energy density of the nucleus is approximately 10 million times greater than the energy density of the electrons that orbit around the nucleus, which is chemistry. So electrons, chemistry, 1 electron volt. Nucleus, nuclear, 4 to 100 million electron volts, 4 to 100 million times larger energy density. So, and just think of what that means. Think of the volume of your gas tank in your car. Now I'm going to say you can do the same thing in that gas tank in a millionth of the space or in a millionth of the mass. It's a pin ahead. That's the important thing. So people talk about cars with a range of 10,000 miles rather than cars with a range of 200 miles. That's a game changer. And a laptop, I've been ridiculed by my friends for bringing up this example, but I'll bring it up again. A laptop that was powered for its use, and when it ran out of power, you tossed it away and got a new one. I think of how that would change society.
Well, as long as we recycled all waste, then that would be good, right?
Well, not throw it away. Recycle it gracefully. Yes.
Thank you. Thank you. Okay.
I'm not quite sure what the difference is, but.
Well, throwing away implies that it's just on a trash heap, and never, we try to forget it.
Throw it into the recycle bin, like
Yes.
the computer laptop recycle bin. You get a credit. You get $100 back.
Well, I think I got all my questions.
Brilliant. My bottom's getting numb.
Oh, good. I'm sorry. Thank you so much.
Oh, no, thanks.
I'm
No
so
problem.
grateful that you did this.
Cheers,
Thank
Ruby.
you.
Thanks.
No problem. Thank you.
That was good. It was really